So we're going to start talking about quadratic functions. And as you know, I think you've studied these quite a bit before. The graph of a quadratic function is a parabola. So let's just think about the properties of a parabola that we might be interested in. So the most important thing is the vertex, right? That's where it changes from decreasing to increasing or increasing to decreasing. Some other properties that are interesting are the x-intercepts, the y-intercept, the axis of symmetry, right? Quadratics are symmetric about an axis, and if that axis goes through the vertex. So if you know where the vertex is, you know where the axis of symmetry is. We might be interested in how much the parabola was stretched vertically or horizontally. So those are all things that we'll be thinking about as we think about graphs of quadratics. All right, so let's look at this parabola. Let's determine what we can about it. So the vertex we can just look at, it looks like it's at 3, 1, right, this point here. So the axis of symmetry would be through the line x equals 3. And its y-intercept, we can just look, it's here at 7. And it has no x-intercepts, right? Some parabolas don't have any x-intercepts. And I think that's what we wanted to find out. So we could just look at this graph and be able to easily see those things because they made such a nice graph for us. There are two forms of quadratic functions, and both are very useful. All right, so the first is called the general form. F of x equals ax squared plus bx plus c. Okay, so a, b, and c are real numbers, and this can't be 0. Sometimes the b and the c could be 0, but this leading term, the coefficient of this x squared, cannot be 0. So that might be the form we're most used to. That's called the general form. And then there's something called the standard form. Okay, we've just rearranged the equation to be in this form. F of x equals a times x minus h squared plus k. All right, and why is this useful? Well, if our toolkit function, if our parent function our base function is f of x equals x squared, we can use what we know about transformations to look at this and know exactly what this is going to look like. Okay, so this x minus h means that the graph has been what? That means that it has been shifted to the right by h units. Okay, and this k on the end means that it's been shifted up, transformed up by k units. So the vertex that used to be at 0, 0 is now at hk, right? So we can look at this form and know exactly where the vertex is, and that's why this form is sometimes called the vertex form. So this is called the standard form or the vertex form of a quadratic function. And then we've got this a here out front. This is actually the same a as that function, okay? And this tells us if the function has been vertically stretched or shrunk, and also if it's been reflected about the x-axis, right? If this is negative, if a is negative, the parabola has been reflected down, and so it opens down. So a negative leading term means the parabola opens down, and a positive leading term means it opens up. Okay, so what if we have it in general form? Can we find the vertex? Yes, we have this handy little equation here. This can be pretty easily derived, and your book does it. We're not going to do it in this video, but if you're interested, you could look at your textbook, and that shows you how you get this value. H equals minus b over 2a. Okay, remember h is the x value of the vertex. So if you had a function in general form, you could say minus b over 2a is going to give me the x value of the vertex. Okay, and there is another equation to find the y value, but it's very complicated and not worth memorizing, because once you know the x value, you can always plug it into your equation to find the y value. Right? The y value is f of minus b over 2a. All right, so if we had an equation like this, x squared plus 4x plus 3, what can we tell about it just by looking at the equation? Well, it's going to open up because there's a positive leading coefficient, and it hasn't been vertically stretched at all. the vertex is going to happen at minus b, so minus 4 over 2a. So minus 4 over 2, so at minus 2. Is that what happened? Yep, minus 2. And then what's the y value? Well, we could put minus 2 in here. We'd get 4 minus 8 plus 3 is minus 1. Sure enough, there's the vertex, right? And there's the axis of symmetry. We'll talk about finding these roots in just a minute. And also the y-intercept is 3. Notice if we plug at the y, for the y-intercept, the x value is 0. That always happens for the y-intercept. Plug 0 in, the y-intercept is 3. Right? So we can see all those things quite easily from the general form of this equation. How about if it's in vertex form, what can we see? Well, before we even look at the graph, although it's right here, let's see, we know it's going to open down because the leading coefficient here is a negative sign, is minus 3. The leading coefficient has a negative sign. So, and it looks like it's also been vertically stretched, right? 3 is bigger than 1, so that's a vertical stretch. So we're a reflection and a vertical stretch. And sure enough, we can see this is kind of like a long, narrow parabola. And we know that the vertex is going to be at negative 2 plus 4. Sure enough, there's the vertex, negative 2 plus 4. We can't as easily see the y-intercept here. I mean, we can just plug in 0 for x. We're going to get, so if we do that, we'll have negative 3 times 4. So negative 12 plus 8. So yeah, the y-intercept is at negative 8. And again, we'll talk about x-intercepts in just a minute. All right, so let's look at this equation, this function, this graph, and write an equation. So this is going to be a transformation of x squared, just like every parabola. And they want us to write it first in vertex form or standard form, and then to expand it and write it in general form. So let's do that together. Here we go. Let's find this equation. All right, so here's our graph. So let's see, we can see the vertex is the formula is going to have the form y equals a times x minus h plus k. Right, and h and k we can determine by looking at where the vertex is. Well, the vertex is at negative 2, negative 3. So x is negative 2, or h is negative 2. So we're going to have x plus 2, right, minus negative 2. And then k is negative 3. Okay, and we can get that just from looking at the graph. How can we figure out what the vertical stretch is, what this a value is? Well, we can just plug in a point on the graph. Let's plug in this point here, 0, negative 1. All right, so our x value is 0 and our y value is negative 1. Oops, sorry, I forgot the important thing. This is a quadratic, it's squared. Sorry. Okay, so what are we going to get? Negative 1 equals 4a minus 3. So I will add 3 and I'll get 2 equals 4a. So I get 1/2 equals a. And just as we expect, a is positive, right? Because the parabola still opens up. There haven't been any reflections. So we could write this as y equals 1/2 x plus 2 squared minus 3. Okay, so that is the standard form of this parabola, the equation of this parabola. Let's find the general form, meaning we have to multiply things out. So we'll have x squared plus 4x plus 4 minus 3. So we'll have 1/2 x squared plus 2x plus 2 minus 3. So we'll have 1/2 x squared plus 2x minus 1. So that would be the general form of this equation. And yeah, we can easily see the y-intercept is negative 1. And we could find the vertex minus b over 2a would be minus 2 over 2 times 1/2. So minus 2 over 1, which is minus 2. Sure enough, that's where the vertex is. That's the x value of the vertex, right? And we could plug this back in for x to find what the y value was if we wanted, but we already know it, right? It's -3. We can look at this equation, the standard form, and we could easily see it's -3, right? So that's how you can go from a graph to the standard form, quite easy. And then it's just some multiplying things out to go from there to the general form, okay? Great. All right, so here they're giving us a general form, and they're asking us to go the other way. We just went from a standard form to a general by just multiplying things out. And now they want us to go from this equation, the general form, to a standard form. So let's do it. All right, find the vertex of this quadratic equation. So first, let's just find the vertex. What if they just asked us to find the vertex? It's going to be minus b, the vertex. Is that too far over? There we go. Is minus b over 2a. So minus -6 over 2 times 2. So it's going to be positive 6/4 or 3/2. Right, that's the x value of the vertex. And now to find the y value, we could put that in f of 3/2 is going to be 2 times 3/2 squared minus 6 times 3/2 plus 7. All right, so we're going to have 2 times 9/4 minus 18/2 plus 7. So 9/2 minus 9 plus 7. So 9/2 minus 2. So it's going to be 9/2 minus 4/2. So 5/2. So our vertex is going to be at 3/2, 5/2. Not too terrible. We can definitely find it from the general form of this equation. But now they want us to rewrite it in standard form. All right, we're going to do this 2 different ways. Standard form we know is going to look like this. Y equals a times x minus h squared plus k. And we know h and k, so y equals a times x minus 3/2 squared plus 5/2. Yeah? And our a is going to be the same. We know that this a is going to be 2. Y equals 2 times x minus 3/2 squared plus 5/2. All right, so we could find the vertex and then write this in standard form. Okay, what if we didn't want to find the vertex? Can we just algebraically go right from here, y equals 2x squared minus 6x plus 7, into standard form? Yes, we can. All right, so here's how we can do it. We factor out this number from these first 2 terms. So we write this as 2 times x squared minus 6x plus 7. Okay, and I'm leaving a blank there. I wish I could write this as x minus or plus something squared. I need this to be a perfect square. Okay? Let me grab a different color pen here. So this is just a quick, I don't know if you've done this before, completing the square. Okay, if this looks familiar, great. If not, we're going to do it a bunch later on. Don't worry about it too much now. But in case you have, what do I need to put here to make this a perfect square? I divide this by 2 and square it. Okay, so minus 6 divided by 2 squared is 9, right? So I write this as plus 9. What have I really added here? Have I added a 9? I've really added an 18. So I have to subtract 18, right? Plus 18 minus 18. So the good thing is, the next step, I can write this as x minus 3 squared. Oh, I totally messed this up. This is supposed, when I factored this 2 out, this was supposed to be a 3. So when I divide it by 2 and square it, 3 divided by 2 squared is 9/4, right? So it's not 9, it's 9/4. And I've really added, what, 9/2. So I need to subtract 9/2. I'm sorry, I messed that up. Okay. So I have a plus 7 minus 9/2, right? This plus 7 is from there. So this is 2 times x minus 3 squared. What's 7 minus 9/2? Well, it's going to be 14/2 minus 9/2 is 5/2. And there we go. I've completed the square. That was super fast and kind of messy. Probably convinced all of you to never do that again. And I don't think you really have to. So don't worry too much if that completing the square part stressed you out. I guess it was there. You can always do it this way. Find the vertex, and then these a's are going to match, right? But you can see both of these ways we got the same equation. All right, let's talk about the domain and range of a quadratic function. All right, here we've got a function x minus 2 squared plus 1. The vertex is at 2, 1. Sure enough, it opens up because this is positive and it hasn't had any vertical stretches. So what is the domain of this function? Well, the domain of any polynomial is all real numbers. Okay, so the domain of any quadratic is always all real numbers. And what's the range? Well, it opens up. So it's going to be the vertex point, the y value of the vertex, 1 to infinity. Right? How about this one? Here the vertex is at negative 3, 4. Yep. And it opens down because of this negative leading coefficient. So if a parabola opens down, it's going to be the y value of the vertex to negative infinity to the y value of the vertex, right? So this will be from negative infinity to 4. This will be from 1 to infinity. And we can also talk about the minimum and maximum values, right? It's always going to happen at the vertex, right? The minimum value is 1, and it happens at x equals 2. Here, the maximum value is 4, and it happens at x equals negative 3. All right, so let's try this one. Example 4. Let's go over to the .cam and find example 4. Find the domain and range of this function. Okay, well, the domain, we know, if it's a quadratic, the domain, we can say, is all real numbers. We could also write that as negative infinity to infinity. Either of those would be right. All right, but how about the range? Well, let's just think this is going to open down. It's going to look like that, right? So the range is going to be from negative infinity to whatever the y value of that vertex is. All right, so let's find the vertex. The vertex is going to happen, the x value is going to be at minus b over 2a. So minus 9 over 2 times negative 5. So it's going to be at 9/10. Is that the answer? No. That is the x value of the vertex. Do we care about the x value to find the range? Not really. But now we can plug this into our original equation. So f of 9/10 is minus 5 times 9/10 squared plus 9 times 9/10 minus 1. So work this out. What do we get? write that as 20, so minus 81 twentieths plus, this is going to be 162 twentieths minus 20 twentieths. Normal person would use a calculator. Minus 81 plus 162 is 81, minus 20 is 61 twentieths. So that is what? That is the y value of the vertex. This vertex happens at 9/10, 61 twentieths. So what is the range? The range is going to be negative infinity up to 61 twentieths, the y value of the vertex. All right, so now let's talk about finding the x and y intercepts. So does every quadratic have a y-intercept? Yes. There's no way that a parabola can't cross the y, it doesn't cross the y-axis. It always does. But how about x-intercepts? How many x-intercepts does it have? Well, it might have 0, right? If it was opened up and was above, or maybe it opened down and was down here. It could have 1 if it exactly touches the x-axis, or it could have 2, right? If it crosses over the x-axis anywhere other than the vertex, it's going to have 2 x-intercepts. So let's do some examples finding the x and y intercepts of parabolas. Organized here. All right, let's look at example 7. Find the x and y intercepts of this quadratic function. Okay, the good news is the y-intercept is always easy. You just find f of 0, and it's negative 2. Okay, the x-intercepts are a little bit harder. We've got a few different ways we can solve this. Okay, that means if the y-intercepts happen when the y value is 0. So we have y equals 3x squared plus 5x minus 2. There's 2 main ways we can solve this, right? One is we could factor it. If it can easily be factored, we can always factor this and set the factors equal to 0. Sometimes works, sometimes doesn't. It always works to use the quadratic function, right? Y equals minus b plus or minus the square root of 2ac b squared minus 4ac all over 2a, right? This is on the ceiling in our room. Minus b plus or minus the square root of b squared minus 4ac all over 2a. So, and here we've got a, b, and c. So let's find these values. And sorry, it's not x. It's the x values equal that. So x equals minus 5 plus or minus the square root of 5 squared minus 4ac all over 2a. As always, be careful of minus signs. Minus 5 plus or minus the square root of 25 plus 24. Is that right? Yep. All over 6. So we get minus 5 plus or minus the square root of 49 all over 6. That's lovely. That's a perfect square. So it's minus 5 plus or minus 7 all over 6. So let's see, one value is minus 5 plus 7 over 6, which is 2/6, which is 1/3. And the other is minus 5 minus 7 over 6, which is minus 12 over 6, which is minus 2, right? Great, so those are our 2 x values of our x intercepts. Okay, that's where the graph crosses the x-axis. What if we didn't want to use the quadratic formula and we wanted to factor this instead? Okay, well, we want to break this middle term apart. We're looking for things that multiply to negative 6 and add to 5. Well, how about 6 and negative 1? Right? Those multiply to -6 and they add to 5. So I'm going to write this as plus 6x minus x. Right? So I've just rewritten this 5x as these two terms. And now I can factor out a 3x. I get x plus 2 minus x plus 2. Perfect, these match. And I'm left with 3x minus 1. Great, I've factored this, and now I can set each of the factors equal to 0, and I get x equals minus 2. 3x minus 1 equals 0. I get x equals 1/3. Same thing. Which is easier? I don't know. Factoring things when the leading coefficient isn't 1 is like a little bit tricky. You got to think about it. So I don't know, maybe that one, in this case, using the quadratic formula might be more straightforward. It's up to you. What about this one? Find the x-intercepts of this function. F of x equals 2x squared plus 4x minus 4. How should we do it? Well, we know that the y-intercept is going to be -4, right? We can just look and see that. So we could write y-intercept is that y equals 4, or -4, sorry. Wait, is that true? I think I'm making this a little bit too easy. What happens if we put in 0 for x? Yep, sure enough. 0 plus 0 equals -4. So this being a leading coefficient of 2 isn't a problem. How about the x-intercept? We're going to have to either factor or use the quadratic formula. So let's see. We're going to say 0 equals 2x squared plus 4x minus 4. Can I make this any easier? I could factor a 2 out of every term. That's going to look like that. So then I could divide everything by 2 and just get x squared plus 2x minus 2. All right, that's nice. That looks like maybe I could factor it pretty easily. I'm looking for things that multiply to -2 and add to +2. Nothing comes to mind. So let's use the quadratic formula. X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So minus 2 plus or minus the square root of 2 squared minus 4ac all over 2a. All right, so what do we get? 4 plus 8 all over 2. The square root of 12 all over 2. Can I simplify this at all? Yeah, I could write this as minus 2 plus or minus, let's see, this is 4 times 3, right? So a 2 can pop out. 2 times the square root of 3 all over 2. So I get x equals minus 1 plus or minus the square root of 3. All right, so are these real? Yeah, that's a number. Those are two numbers on the x-axis. I would probably never have been able to factor this and guess these numbers, right? So in a case like this, where you have irrational roots, meaning like square root of 3 isn't an easy number you could write as a fraction. These are irrational roots, but they're real. So really the quadratic formula is the only way you could find this realistically. But those would be the two x-intercepts. All right, let's do one last problem like this. Example 9, they say solve this using the quadratic formula. X squared plus x plus 2 equals 0. All right, so we know here they're not asking for the y-intercept or anything. They're just saying solve. Really, that's the same thing as asking for the x-intercepts of this graph. Solving it, if it's equal to 0, means find the x-intercepts. So what are we going to get? X equals minus b, so minus 1 plus or minus the square root of b squared, 1 squared, minus 4ac all over 2a. So I'm going to get minus 1 plus or minus the square root of 1 minus 8 all over 2. So minus 1 plus or minus the square root of minus 7 all over 2. It's square root of a negative number, that looks like an imaginary number. And sure enough, it is. So we're going to have minus 1 plus or minus I times the square root of 7 all over 2. Okay, so let's write this in standard form. Minus 1/2 plus or minus the square root of 7 over 2 times I. Those are the solutions to this equation. What does that mean, complex roots? Well, let's think of what this parabola is going to look like. It's going to open up, right? And we can't easily see, I don't know exactly where the vertex is going to be, but I do know it's going to be above the x-axis. Okay, this does not ever cross the x-axis. It has no roots, no real roots. It has complex roots. It has imaginary roots. Okay, there's not like an easy standard way to relate this to the graph. Okay, what it does mean is it does not cross the x-axis. Okay, so those are some examples of solving quadratics where we get 2 roots, 2 irrational roots, and here we got 2 imaginary roots. Okay, so 0 real roots.